So as you just saw, this is a very common method of collecting any sort of gas. You generate it in a tube like this right here, and then it goes through the hose and you collect it over water. The only thing is that it's not pure gas. Some water evaporates, and now you've got a partial pressure situation because you have a mixture of the gas you generated and some water. If you look at this little blow up here, it has the red particles, which in this case would be the gas I generated, and a couple blue particles, which would be the water. Now, it's a little bit skewed. I don't think that this would be a 3 to, 7 gas particles to 3. It's probably not that high of a ratio. It's a lot less than that usually. There's a lot less water than the gas you generate, but it gives you the idea. Look at this. You got a whole host of equations here to look at. Quite a busy slide, but let me just quickly run through it. The first equation that you see there is the ideal gas law. The only thing I've done differently here is I've put the word total and all that, but typically we've just written that one as PV equals nRT. So nothing really different there. Just want to remind you that if you measure the total pressure of all the gas in there, total volume is what the gas takes up, you're going to get the total moles if you solve between those ones. And of course, all the gases in a mixture would be at the same temperature, you would think. What I was doing though is I split it up, and I have one version here where all I did was I replaced the total there with the amount of hydrogen here, and so I can adapt the ideal gas law to the different gases that are there. So there's one version of the thing for if I'm talking about hydrogen, and here's the version if I'm talking about water. All right, and so here's the one thing to keep in mind. Even though I wrote V of water and VH2 in those equations, like right here, let me see if I can circle it. So right here I wrote VH2 and V of water right here. So even though I did that, I didn't really have to, because think about the space that you see in this little spot here inside that flask or that little collection tube. The volume that those gases takes up is exactly the same. So the total volume is going to equal the volume that the water gas takes up, which is really the same volume that the hydrogen gas. Now in reality, gas particles take up space, but because we're modeling things as ideal gases here, we are making some assumptions that gas particles don't really take up space. It's not that big of a deal in that case. Now, of course they do, and in some conditions it can throw things off, but we are going to make that assumption, okay? And then the other thing to keep in mind here is that the total moles of gas that's inside that container is equal to the moles of the hydrogen gas plus the moles of the water gas. So how do I get a value for the partial pressure of water in a mixture like this? If I want to know about the gas that I was supposed to be generating, and now there's some water vapor in there. Well, P water, you've heard of it called the partial pressure of water. The other term, though, that you may hear it called is this, the vapor pressure of water. So when you're looking for these values, or someone has described them, they are interchangeable, these terms. Partial pressure of water, or you can look up the vapor pressure of water. So how do we get the value? Well, you would get it by doing this. Look it up. You can find a table that would have this based on water's temperature. Do a quick Google search and look up vapor pressure of water table or partial pressure of water table. And here's one I found on the internet. It looks like a picture that someone took, of a book or something. And you can see it has different temperatures listed and different pressures, vapor pressures of water. And so the partial pressure of the water in those mixtures is dependent on the temperature. So if the temperature of the gas in there that was above the water was, let's say, 21 degrees, well, then the partial pressure of that water would be 2.5 kilopascals. If the temperature of that water, let's say that the gas was 10 degrees, the partial pressure of that water would be 1.2 kilopascals. You can find these tables anywhere. All right, a partial pressure collection of gas over water problem. First thing I see here is the volume. I'm going to collect this gas over water, and I first get 300 milliliters. The temperature of this gas or water mixture, whatever, is 20 Celsius. Right away, I'm going to convert it to Kelvin, 293.15 Kelvin. And the room pressure is 760, which that tells me the total pressure of this water gas mixture inside the upper part of this flask here is actually 760. Otherwise, the water level would be changing if it wasn't exactly the same pressure in that flask as it was in the room. And the question's asking how many grams of hydrogen are in the flask. All right. So let me just move things around a little bit. I do have to watch out for that volume. Bring in this table here. I see that the water temperature, or which I'll assume is the same as the gas temperature, is 20 degrees. So looking at my table, I see, let's see, where are you? Temperature 20, there it is, in the very first column, in the very bottom row. You see temperature is 20 degrees Celsius, partial pressure is 2.3, careful, kilopascals in this case. So I got to write it as 2.3 kilopascals. And looks like I have a conversion to do here. You know, I've got this in 2.3 kilopascals, but my total pressure is in millimeters of mercury. So I think what I'm going to do here is convert this right away from kilopascals to millimeters of mercury, and I will use the corresponding conversion to do so. And so what do I get for the partial pressure of water in the mixture? It is 17 let's round, 0.3 millimeters of mercury. Okay, so that total, that 760 millimeters of mercury is the collisions of the water plus the collisions of the hydrogen. I just want the partial pressure of the hydrogen. I just want the collisions caused by the hydrogen. So what I need to do here is set up an equation. The partial pressure of the hydrogen equals the 760, which was the total pressure of the gases, or all the collisions, and I'm going to subtract off the collisions from the water, which is 17.3, or the partial pressure of the water. And so I get a partial pressure of hydrogen. Let's see, it's 742.7 millimeters of mercury. Okay, I'm pretty much set. The one thing I haven't done yet is my volume. I left it as 300 milliliters. I need to make sure I use 0.3 liters. But here we go. I can use the ideal gas law. Right now as written, it means the total of everything. So I'm writing in H2 here by the pressure, because I'm going to sneak in the partial pressure of the hydrogen, and therefore I will get the moles of hydrogen. So here we go. 742.7 millimeters of mercury of pressure for the hydrogen. I'm going to multiply that by the volume. I'm going to do a quick conversion to liters. It's 300 milliliters is 0.3 liters. I'm going to solve for N here, the moles of hydrogen. The R value I'm going to use is 62.4 liter millimeters of mercury mole Kelvin, because my partial pressure of hydrogen is in millimeters of mercury. So I'm going to pick the appropriate units, and I'm going to use my Kelvin temperature here for the ideal gas law, 293.15, and I can solve for the moles of hydrogen that are above in that flask. Okay, and when I do the math here, and I just multiply 742.7 times 0.3 divided by 62.4 divided by 293.15, I get that there are about 0.0122 moles of hydrogen in there. Now, the question is actually asking for what is the mass of hydrogen, not the moles. But hopefully you remember the easy part. How do you convert moles into grams? So I'll rewrite that down. 0.0122 moles of H2. And every 1 mole of H2 is 2.02 grams of H2. So we'll just do a little multiplication here, and I get a final answer of 0.0246 grams of hydrogen gas that was collected here. And maybe I can just rezoom here a little bit just so you can kind of see the whole And let's see, here we go. The whole amount of work that went into this one question. Here you go. So what I'm going to suggest that you do for this question is to pause the video and then unpause and see me work through the solution. So go ahead and pause. Okay, and now I'm going to work through the answer here. So we've got helium is collected over water at 25 degrees and 1 atmosphere of pressure. What total volume of gas must be collected to obtain 0.586 grams of helium? So I'm going to start writing numbers down. Got a temperature. Just going to convert it to Kelvin right away because I know I'll use it. And I have a pressure. I'm going to put PT for total pressure. 1 atmosphere. I know there's kilopascals in the table, and 1 atmosphere of pressure is the same as 101.3 kilopascals, so I'll put that in. Next thing here, looking for the volume. Now this is interesting because the volume of the water gas is the same as the total volume, which is the same as the helium gas volume. All right, and I'm also given the mass of helium that I want, and it's 0.586 grams. All right, so let me first get this to moles. Convert this helium into moles of helium that I want. So I'll start with the 0.586 grams of helium, and the molar mass of helium is 4 grams. Okay, so 4 grams, 1 mole. I just divide by 4 here, and I'm going to get 0.1465 moles of helium is what I need. All right, the other thing I want to do is, since I'm solving around helium for this, I'd like to know what's the partial pressure of just the helium. What collisions are due to helium? So I can do that here by, the water plus the helium collisions have to equal the total pressure. So in other words, partial pressure of helium is the total pressure minus the partial pressure of the water. Let me look up. Let's see, what's the partial pressure of the water? We're at 25 degrees. Let's see, zoom in a little bit more there. 25 degrees. There it is. Don't know why I couldn't find it. It is 3.2 kilopascals. So I'll write that down. Partial pressure of water, 3.2 kilopascals. The total pressure of the water was 101.3 kilopascals. So just a little bit of subtraction here to give me the partial pressure of the helium, and I have 98.1 kilopascals. Okay, now I've got enough to do the ideal gas law just around helium in the mixture with the helium and the water. Okay, so I'll write down the ideal gas law, PV equals nRT, and then I want to make it specific to helium. I'll put the HE by pressure, and that'll give me the moles of helium, or vice versa, okay? Now the volume, you might think of, well, it's the volume of helium. That's right, it is. But remember, the volume of helium is the same as the volume of the water vapor, which is the same as the total volume. They take up that whole space. So I'll just plug in the numbers I have, making sure I use the partial pressure of helium. The moles of helium is there. Because I'm using kilopascals, I'm going to use 8.314 for R. And then lastly, I need my Kelvin temperature for this to work. And that is 298.15 Kelvin. All right, so what I'm going to do is I'm going to multiply those three numbers on the right side of the equation and divide them all by 98.1, and I get a final answer of 3.7 liters. And let me just zoom here so we can kind of see all the work together that went into that question. There we go.